and technology. And then we had started with our discussion on space science. We discussed everything about the universe and various aspects of it. And then we had moved on to our discussion on celestial bodies, where we discussed about stars, black holes, and the sun. So that is where we had stopped in the last class. So today, as we begin, the first class or the first topic that we have today is about our planets. So we'll discuss about the planets, we'll discuss about the other celestial bodies like asteroids, meteoroids, or comets, etc. And then after that, we'll move on to the second part, that is space technology, where we'll discuss some of the basics related to the launching of the satellites and various aspects of satellites and the orbits. So these are the things that we are going to discuss in today's class. All right, so let's begin. Now, first and foremost, when we talk about planets, we need to understand how do we define a planet. All right, so as far as the definition goes, there are a couple of things that are seen as criteria for any celestial body to be defined as a planet. So what are the criteria? First, that it orbits the sun, right? So the first thing would be that it has to orbit the sun, or let's say if it is a planet outside our solar system, then for that matter, any other star. It has to orbit around any other star. Then after that, it has sufficient mass for spherical shape. So as we had discussed about the stars as well in yesterday's class, we had discussed that in cases of stars also, the stars are having a spherical shape because of their gravity, and the gravity comes from their mass, the inner mass that any star has. Similarly, for a planet also, it has to be having a good enough mass so that it can also be spherical in shape, or let's say almost spherical in shape. And then the third point is about clearing its orbit. Now, what do we mean by clearing its orbit? We need to understand this third point. The first 2 points are pretty easy to understand, but the third point could be a little difficult point to understand. Now, when it comes to the third point about clearing its orbit, it simply means that there should not be anything in the vicinity. In the surrounding areas, there should not be any celestial body that has its independent existence. Meaning that if you have another celestial body near this planet, then that celestial body should be revolving around this planet. It should be revolving around its planet, just like, for example, our moon. It is very near the earth, but it revolves around the earth. It does not have its independent orbit. It should not be orbiting independently around the sun, but instead it should be always revolving around the earth. That is what we mean by clearing the orbit, that you should not have anything that has an independent existence around this planet. Now, why did we add this criteria? This criteria is something that was just added in 2006. Until 2006, only the first two criteria were taken into account for defining any celestial body as a planet. But then this third criteria was added in 2006. And this is where the number of planets in our solar system went down from 9 to 8. So this is where we saw that Pluto ceased to remain as a planet, and it was reclassified as a dwarf planet. Pluto was reclassified as a dwarf planet. Now, what do we mean by a dwarf planet? Now, dwarf planet basically is any planet or any celestial body that satisfies the first two criteria and doesn't satisfy the third criteria. All right. So, satisfies the first two criteria doesn't satisfy the third criteria. So in such a scenario, you will say that it's a dwarf planet. So Pluto then became a dwarf planet. Pluto then became a dwarf planet. Now, there is an interesting story behind Pluto being reclassified as well. There's another dwarf planet called as Aries. Aries was discovered. All right. So until then, there were 9 planets in the solar system, and Pluto was the ninth planet. And then we discovered Aries. Now, Aries was also spherical in shape. Aries was also revolving around the sun, and the size of Aries was determined to be bigger than Pluto. So now the discussion started, the debate started, that it's bigger than Pluto, it is also round in shape, it is also revolving the sun. Then why not classify Aries also as a planet and make Aries as the 10th planet of the solar system? But then many of the scientists were of the belief that this planet system should be an elite class. It should be just a limited number. And tomorrow you'll discover something else and you will start describing that also as a planet. You might discover an 11th or a 12th or a 13th planet, and so on. So let's do something so that this remains a small list and the list does not just keep on getting bigger. So then what happened there is that Pluto and Aries, these are two planets, or let's say these are two celestial bodies which are very close to one another. All right, they're very close to one another and they have their own independent existence. It's not that Aries is revolving around Pluto or Pluto is revolving around Aries. Both of them have their independent existence and have their orbits around the sun. So then they thought that, okay, fine, let's add this third criteria, that they should have an independent exist. They uh, should have an independent existence and they should not be surrounded by anything else in their vicinity. So this is where the third criteria was added, because Aries was discovered and Aries was said to be seen to be bigger than Pluto and also revolving around the sun and also round in shape, and hence this all discussion and debate started. Later on, this was I think Voyager 2, when it was sent almost 2015-16. This is where they found that Aries is actually smaller than Pluto, that the initial calculations, initial observations were wrong, and Aries is actually smaller than Pluto. But by that time it was very late for Pluto. Pluto already was classified as a dwarf planet. So unfortunately this was a wrong observation, for which Pluto lost its planethood. Otherwise, Pluto would still have remained as the ninth planet of the solar system. So, unfortunate for Pluto. Many are still looking for justice for Pluto. If you go on Instagram, there actually are hashtags which say justice for Pluto, and there are many people who are actually fighting for this justice. There are scientists also who keep raising this point from time to time, and there are others in science who are also challenging this, that Pluto should be reclassified as a planet. So there are a lot of people who are a part of this wagon, and I'm proud to say that even I'm a part of this wagon. So but the stories aside, this is what the scenario is right now, that for anything to be classified as a planet, you need these three criteria. And the third criteria, clearing its orbit, I'm just writing this in detail. There shouldn't be any other celestial body near a planet having an independent existence. All right. So this is what we mean by the third point. So that's why Aries and Pluto, and there is Ceres as well. I'm just writing the name. You have Ceres, sorry, Ceres. So all these are examples of dwarf planets. Apart from that, we have another term that we use called as exoplanets as well. Exoplanets. So exoplanets basically are the planets which are outside the solar system, right? So I'm just mentioning it here. Planets outside the solar system. So all the planets that are outside the solar system, they are called as exoplanets. So in this manner, this is how we basically look at planets. Now, so Pluto no more is a planet. Pluto now becomes a dwarf planet. Now, when it comes to the planets, there are certain things that can become important from the perspective of the examination, because there are certain points which are unique about each and every planet. So there are certain things that you should know strictly from prelims perspective about the planets, and I'm sure that there are many of these facts that you already probably are aware of, but still, I just for the sake of your examination, there are chances, because I'll tell you something, a change, or rather, let's say, a revisit of a pattern that I've seen in the papers. uh, Questions based on celestial bodies, planets, sun, comets, asteroids, etc., they used to be very common and very popular in UPSC civil services, as well as your state level examinations as well. But after almost, I would say, 2011, 2012, we saw a gap, that they were not asking any questions based on celestial bodies, one of their, we would say, favorite subjects or favorite topics. But last couple of years they have started revisiting it. A question on sun has been asked, a question on other celestial bodies has been asked, and very likely they are going to revisit all these areas again, because now they have uh, revisited the topic once, and it means that they probably will stick around this topic for a while. So uh, that's why I would say that this could be an important topic from that perspective. So there are certain things that are important. So just mentioning those points here, that for example, let's say if we talk about Mercury. Mercury is the closest planet to the sun, right? This is the closest to the sun. Now, about Mercury, this is one very, very important point. Now, if I ask you, I have a question for you. Can you tell me which is the hottest planet of the solar system quickly? Which is the hottest planet of the solar system? Yes, most of you are absolutely correct. The hottest planet is Venus and not Mercury. Although Mercury is the closest planet to the sun, but still it is not the hottest planet of the solar system. All right. So that is where Venus becomes an important uh, planet, that this is the hottest planet. And can you quickly tell me why it is the hottest planet? Why is it the hottest planet? Yeah, correct. So most of you have given the correct answer. This is mainly because of the presence of carbon dioxide in the atmosphere. Presence of carbon dioxide in the atmosphere, that makes it the hottest planet. Do you know how much it is? It's almost 95.5% carbon dioxide in the atmosphere. How much does the Earth have? What's the percentage of carbon dioxide on our planet? Yes, 0.04, 0.03. It's exactly 0.038%. So you can say that it's almost 0.04. So just imagine that with 0.04% of carbon dioxide, we are screaming about greenhouse gas effect, global warming, and so on. And just imagine when this percentage is 95.5. So the greenhouse effect on Venus is very severe, and that makes it the hottest planet of the solar system. All right. So that's why Venus is the hottest planet and not Mercury. Now, about Venus, there is something else which is very crucial, and this is the fact that its rotational motion is opposite to the rotational motion of most of the other planets. So, for example, let's say when you take the Earth or many of the other planets, you'll see that all these planets, they are revolving from west to east. Sorry, rotating. They are rotating from west to east. But Venus is a planet which is rotating from east to west. All right. Venus is a planet that rotates from east to west. So that's why this is very, very important. Rotates from east to west. It is also called as retrograde motion. So it is believed that maybe during the formation of the solar system, the early part of the solar system, it might have collided with some other celestial body, and that might have changed its direction of motion. It is believed so. We don't know for sure, but it is believed that this might have happened, changing the direction of motion for Venus. So it rotates from east to west. Now, if I ask you another question, do you know which is the densest planet of the solar system? Which is the densest planet of the solar system? And let me give you four options. You have Venus, you have Mercury, you have Earth, and you have Jupiter. I'm quickly giving you 10 seconds, launching a poll, and give me the correct answer quickly. Just a planet, just one of these planets in the solar system. We forget, because we know that we have become very special as a species. So we forget that we are looking, what we are living at is also just one of these planets. So Earth is the densest planet of the solar system because of presence of metals, a lot of metals that are present on the Earth, that makes it the densest planet of the solar system. Apart from that, Mercury is the second densest planet of the solar system, second. Now what I saw is that many of you marked Jupiter. Now, what we know is, and I have given Jupiter purposely because I knew that the moment I give Jupiter as an option, there are going to be a lot of students who will mark Jupiter. The reason for this is that you know that Jupiter is the biggest planet, right? You know that it's the largest planet of the solar system. So you might think that that's related to density. But always remember, what is the formula for density? Anyone who remembers, what is the formula for density? Yes, correct. Many of you have given the correct answer. It is mass divided by volume, right? Mass divided by volume. So, what do you see with Jupiter? Jupiter has a very high volume. It's big, so it has very high volume, and also Jupiter is a gaseous planet. So gaseous planet cannot be dense. For density, you need a solid surface, right? So that will make a planet dense. So that's why Earth is very dense planet. Mercury is a very dense planet. Even Mars is dense. Venus is. But the other planets, Jupiter, Saturn, Uranus, and Neptune, these four planets, they are gaseous. So their density cannot be high. Density of any gas cannot be high because gas just takes up a lot of space, correct? So that's why density of gas cannot be very high, and that's why Jupiter cannot be the answer. But just because you know that it's a big planet, it will obviously have a larger mass, so your brain quickly goes there thinking that probably this is the densest planet, but actually it is not. Then coming to Mars, I'm skipping the Earth because that's what geography is about. So that's why I'm not discussing about the Earth here. But coming to Mars, Mars is called as the red planet, correct? It is called as the red planet. Do you know why red planet? Why is it the red planet? Iron oxides, perfectly correct. Ravi, I like your answer, USSR, but that's not the reason. So it's the red planet because of presence of iron oxides. Right, presence of iron oxides, the soil basically has a lot of iron in it, so that makes it the red planet. That's why it looks red in color. All right, so for Mars, that becomes an important part. Then Mars, when it comes to all these planets, just remember this, that all these planets, they are also called as inner planets. All right, so there is something called as inner planets, and there are, on the other hand, you have outer planets. So inner planets basically are the planets that you have between the sun and the asteroid belt. All right, between the sun and the asteroid belt, all these are called as inner planets. So inner planets meaning you have Mercury, you have Venus, you have Earth, and you have Mars. So these four will be called as inner planets. So all the inner planets, they basically have a solid surface, right? They all have a solid surface. And the outer planets, they basically are, they have, they are also called as gas giants. They are called as gas giants. Also, one point which is very common between all the inner planets is that they have no rings. They have no rings. And when it comes to outer planets, all the outer planets have rings. They all have rings. All right. So we know about Saturn and the rings of Saturn, and they are very profound and very famous as well. But it's not only Saturn that has a ring system around it, but even Jupiter, even Uranus, and even Neptune, they all also have ring system around them. So that's why they all have rings. So let's say, as a question, I mean, I'm giving you all these facts because if they have to, these are the kinds of facts that they can ask about planets. So they might give you this as one of these statements, that this planet has a ring system or that planet has a ring system. Very clear demarcation. All the inner planets, they don't have rings. All the outer planets, they have ring systems. Also, when it comes to the number of moons, we see that Mercury has 0 moons. Then even Venus has 0 moons. Earth, we know that Earth has 1 moon, and Mars has 2 moons. So the number of moons here is pretty countable for the inner planets. But when it comes to the outer planets, the number of moons is pretty high. And you'll see that the number of moons, this number will also keep on changing from time to time. So recently it has been in the news because until last year, what we knew is that Saturn has the highest number of moons and Jupiter has the second highest number of moons. But all of a sudden, there were 20 new moons that were recognized for Jupiter. And then the number increased to 92. And I think for Saturn, it was 82 at that point of time. So Saturn was 82, Jupiter was 72. Then Jupiter became 92, and Saturn remained at 82. And so Jupiter had the highest number of moons. And then now, significantly more number of moons have been now recognized for Saturn, and the number has gone up to 145, if I'm not wrong, or 146. So now again Saturn has the top spot and Jupiter again has the second spot. So that's why these numbers will keep on changing. So no need to remember the number, that you need not know that this is exactly what the number of moons is, because there will be additions that will keep on happening, or maybe sometimes even subtractions happen, that something that they might have recognized as a moon, they'll later recognize that it's not a moon. So these kind of things will keep on happening. So no need to remember the numbers. Just that just remember that right now Saturn is sitting with the highest number of moons in 140s, if I'm not wrong, and Jupiter second highest with I think 95 being the number. So this is where we are right now. So that's why don't need to remember the the numbers of all these moons. So that's why these are things that are certain things that are related to all these planets. Now also, one of the things when it comes to the other planets, uh, the outer planets that we have. So about Jupiter, we know that this is the largest planet, right? Jupiter is the largest planet of the solar system. Now, when it comes to Jupiter, there is something else which is very famous about Jupiter, and this is about the great red spot that it has. There is something which is called as the giant red spot or the great red spot. So this red spot, although this is something that looks like a spot on Jupiter, is actually not a spot, but rather these are winds. These are winds on Jupiter. So these are winds on Jupiter, which when we look from the telescope looks like a spot on the surface of Jupiter. So that is what we know about Jupiter. Then when it comes to Saturn, about Saturn we obviously know about the ring system and it having the most profoundly visible ring system. But apart from that, as we discussed, that it has the highest number of moons. I'm not mentioning the number here because the numbers will keep on fluctuating, so don't worry about that. Then after that, when it comes to Saturn, Saturn probably has the least density. It is said that the density of Saturn is so less that even if you have water, it will just float on water. It has such less density. So that's why it has very, very less density. If let's say you had a bathtub which is good enough or large enough to hold Saturn, it would just float on that water. It has such a low density. So that is there. But one more thing, that it is also said to be the flattest planet. All right. It is said to be the flattest planet of the solar system. So that also becomes a very crucial information about it. Just give me one moment, please. Flat at the poles and very bulged out at the equators. So that's why we are saying that it's the flattest planet, because the difference between the polar diameter to the equatorial diameter is the highest when it comes to Saturn. So that's why it is called as the flattest planet of the solar system. Then after that, we have Uranus. Now, in case of Uranus, what we know is that Uranus, first and foremost, again, its motion is very well known, because its motion also is very different as compared to the motion of many of the other planets. So, for example, in case of Venus, we know that it rotates from east to west. Now, in case of Uranus, what happens here is that Uranus has a very flat pole, or you can say almost a horizontal pole. So, because of that, what happens is that the uh, rotation of Uranus looks like it is just rolling around the sun, because it has a very flat, uh, I mean, almost a horizontal axis. For Earth, we know that it has a little tilted axis, correct? But in case of Uranus, it is almost a horizontal axis. So that's why it looks like it is rolling around the sun. So that's why, again, this also has a very different rotation. So rotation looks like rolling around the sun. Then, in case of Uranus, also what happens is that sometimes it reaches temperatures which are lesser than Neptune. But that's not the case what we saw with Venus and Mercury. Because in case of Venus and Mercury, we know that Venus always is hotter as compared to Mercury. But in case of Uranus, it happens sometimes that it reaches temperatures which are even lower than the temperatures that are registered on Neptune, although Neptune is the farthest planet. So it does happen sometimes, and it also, again, it happens mainly because uh, when it comes to Neptune, Neptune has a large amount of Neptune has a large amount of methane. So Neptune, many a times, that's why it is also called as the blue planet. It is called as the blue planet because it has large amount of Neptune. Sorry, a large amount of methane. It has a large amount of methane in the atmosphere, and that gives it a bluish color. So that is why it is also called as the blue planet sometimes. So methane, because methane also is obviously a greenhouse gas, so it traps a little more energy, I mean heat, as compared to Uranus. And that is why sometimes what we see is that Uranus can become colder as compared to Neptune. So so these are some of the points that probably can be important, if at all they are going to ask you any fact based prelims question on planets. These are the some of the things that can actually become important. So we know that when it comes to all these planets, there is only one planet which can support life, and that is where we are sitting right now, that is the Earth. Now, apart from planets, there are certain other celestial bodies as well. that can become important. Now, there are three celestial bodies that we are going to discuss here in the next 10-15 minutes: comets, asteroids, and meteoroids. All these three are very similar in their composition and how they look, but there are subtle differences that we have in them. So that's why try to understand the differences between a comet, an asteroid, and a meteoroid. That how do we differentiate between the three? So first we are starting with comets. So among the three, comets is the biggest. All right, it would have the size as mentioned here, roughly the size of a small town, meaning that up to 10 kilometers in radius. All right, up to 10 kilometers in radius is what you would have a comet like. So I'm just mentioning here, up to 10 kilometers radius. All right, so that is what we see about comets. Now, in case of comets, we see that they would be made of certain things. For example, there will be a solid surface, there can be a solid surface, and this solid surface can have dust particles, ice, and maybe sometimes some metal pieces as well. So, all these things it will be made of. And then after that, it will be surrounded by a hydrogen gas, a cloud of hydrogen gas, which in a manner you can say is like atmosphere of comet. So you can say that comet has atmosphere. It has atmosphere made of hydrogen. All right, it has atmosphere made of hydrogen. So there is a hydrogen cloud. You can say that in a manner there is a hydrogen cloud that is surrounding it, that is surrounding this small piece of, you can say, stone kind of structure, where you have maybe metals, ice, dust particles, carbon dioxide, frozen gases, ammonia. All these things can be present at the center and then surrounded by the hydrogen cloud. Now what happens is that in case of a comet as well, the comet can also have a fixed radius, or let's say fixed orbit around the sun. All right, now sometimes it will come closer to the sun, and as it starts to come closer to the sun, this is where we start looking at a comet which also has its tail. Comet is very well known for its tail, right? That there is a very profound tail that you can see on any comet. So that tail basically is made of all these frozen gases, etc., which start to melt and they start to gasify as they come closer to the sun. So that is basically what happens in a comet, and that's why comet will have a long tail. So so it can have dust, ice, carbon dioxide, ammonia, methane. Metals also can be present. So all these things also can be present on a comet. All right, so basically this is what happens. So there are actually two kinds of tails. One is a visible tail and an invisible tail. But the one which is visible, it basically happens because when it comes close to the sun, all these things will start to melt, and that will lead to the formation of this tail of the comet. So in this manner we see that this is how the comets basically can be observed. Then after this we have asteroids. Now, asteroids in size as compared to comets, they are going to be very small. Right? They can be very, very small. Largely, you'll see that they will have a radius of like 100 meters, 200 meters, 400 meters. So, not more, many of them are larger than 500 meters. All right. Most of them will be in this particular range of maximum 3 to 500 meters. Just remember, there we said that it could be up to 10 kilometers in radius. Here we are saying it's only 300 to 500 meters. That's it. Nothing more than that. So, so that's why asteroids, in comparison to comets, are very small. All right, they're very, very small. Now, in case of asteroids, one more thing to be known is that they are very small and they could be made again of anything. They can be made of a metal. They can basically be a metallic asteroid. They can be a carbon-rich asteroid. Very recently, this was also in news. The Osiris Rex mission. Have you read about this? The Osiris Rex mission. Why was it in news? Anyone who knows quickly? Yes. Anurag, you are correct. Anandu, you are correct. Huh. So many of you have given the correct answer. That's great. So basically, it came back with an asteroid sample. The asteroid that it went to, the name of the asteroid is Bennu. And this Bennu basically is a carbon rich asteroid. It is a carbon rich asteroid. Now, Osiris Rex was a sample collect mission. So it went to Bennu. It basically, you can say, blasted off its surface. So it collected samples from its surface, and now it has brought it back to the Earth. Just a few days back, it has brought it back to the Earth. So now we'll analyze the surface, try to understand the composition and everything. So this is what asteroids are. So asteroids could be made of a metal. They can be made of carbon. They can be made of anything that you can say a planet is made of, right? Because it is also believed that the asteroid belt that we have between Mars and Jupiter, it might have been an ancient planet, and this planet might have just broken off into large number of pieces and kept on revolving in the same orbit. So that is what might have happened and might have led to the formation of an asteroid. So that's why asteroids largely are made of everything that a planet will be made of. They will have no atmosphere. All right, there is no atmosphere. So that's why we are saying that it is airless rocky worlds. Airless meaning that it has no atmosphere. It has no atmosphere. So now in these kind of scenarios, we see that asteroids are very, very less in very small in size. So small meaning they can be up to 500-600 meters in diameter. Sorry, let me write it clearly. Up to 500-600 meters in diameter. So very small. All right, very small as compared to comets in most of the cases. All right, I'm writing mostly because there are certain which can be little larger than this. So mostly up to 500-600 meters only. Now, so this is what asteroid is. So comet has an atmosphere. Asteroid does not. Comet is larger. Asteroid is smaller. Comet can be made of mix of a lot of things. Largely, asteroids are made of one single material in most of the cases. So that is how we see that they are different. Then after that, we have meteors, meteoroids, and meteorites. Now here the most important term is meteoroid. All right, meteor and meteorite are two different terms which are given based on the position of a meteoroid. All right, the based on the position of a meteoroid, we see that all these things are placed. Now, when it comes to a meteoroid, meteoroid can be even smaller than an asteroid. It can be even smaller than an asteroid. That in most of the cases they can be just as small as just 10 meters in size. Just 10 meters in size. In most of the cases, meteoroids will be like that. They do not have a fixed path. That, for example, in comets case, we discussed that they have a fixed orbit around the sun, very large orbit, but they have a fixed orbit around the sun. Most of them are outside Neptune, I mean beyond Neptune, but at least they have a fixed orbit. In case of asteroids also, most of them they are between Jupiter and Mars, so they also have a kind of a fixed orbit. In case of meteoroids, that's not the case. They do not have any fixed orbit. They will just keep hanging around in space wherever they want. Now, these meteoroids, they will be made of metals. They can be made of, again, metals. They can be made of iron and nickel in most of the cases. So extraterrestrial nickel and iron is what they'll be made of most of the times. So, and some of the other minerals they also can have. Now, in case of meteoroids, what may happen is that sometimes they might come close to the Earth. And when they come close to the Earth, then in that case, obviously, they will be attracted by the gravitational pull of the Earth, right? So gravity of the Earth will pull it towards itself, and as it pulls it towards itself, this is where this meteoroid will come or will be pulled by the earth, and it will completely burn up in the atmosphere, because earth has a very thick atmosphere and there will be a lot of air resistance because of the high speed of this meteoroid, and it will completely burn up as it enters the earth. In such a scenario, this meteoroid is called as a meteor, right? In such a scenario, it is called as a meteor. But if in case, let's say it does not completely burn up in the atmosphere, and then small pieces, let's say they fall on the earth, or sometimes even bigger pieces can fall on the earth, then in that case it is called as a meteorite. So that's the basic difference, that uh, meteoroid basically is something that will burn up uh, when it burns up completely, when it passes through the atmosphere, it is called as a meteor. And when meteoroid that survives the falling, that will be called as a meteorite. So that's the basic difference. That's the basic difference, that meteoroid is the one that you have in space. Meteor is the one that will completely burn up in the atmosphere as it passes through it. Sorry. And meteorite is something that would fall on the earth. So that's the basic difference between the three. So sometimes that's why meteors, these are also called as shooting stars, right? They're also called as shooting stars, and many people also make a wish when they see a shooting star, and this is probably what also happened to the dinosaurs. If you know about the extinction of dinosaurs, uh, there is something called as mass extinction. So there is something called as mass extinction, and this mass extinction happened mainly because there was a meteorite, or a meteorite number of meteorites that fell on the earth, and because of its falling on the earth, it might have released a lot of dust, a lot of dust particles, etc., and that would have covered the entire earth, blocking the sun rays from entering the earth. That would have stopped the photosynthesis and every other animal that is dependent on that photosynthesis. And that's why the primary consumers, the producers, the primary consumers, the secondary consumers, and all of them, they would have died. And almost, it is believed that almost up to 85% of all the species that were living on the earth at that point of time, they just lost their lives, including the dinosaurs. So that is basically what might have happened, and it ultimately probably would have led to the extinction of the dinosaurs. So uh, so that's why meteorite can be so dangerous, and from time to time you might hear these kind of news, that there is an asteroid that is heading towards the earth, there is a meteor that is heading towards the earth, and the scientists are worried about that, because if at all, if it's a big one, if it comes to the earth, it can lead to a similar fate for all of us that happened to these dinosaurs. So that is why all these things can become very crucial. Look at this question. This question was asked in your paper. Please read the question. Have given the correct answer, which is B, but let me just discuss this with you. What is the difference between asteroids and comets? First is, asteroids are small rocky planetoids. This seems correct, right? Small rocky planetoids. While comets are formed of frozen gases, we discussed that they have frozen gases held together by rocky and metallic material. We discussed that metals can be there at the core of the comet. So this seems fine. This is correct. Asteroids are found mostly between the orbits of Jupiter and Mars. This is fine. This is correct. While comets are found mostly between Venus and Mercury. This is wrong. This should not have been marked as correct, because as we discussed that they have a very long orbit. They, most of them will be outside Neptune, not between Venus and Mercury. Otherwise they would be always visible, right, if they were between Venus and Mercury, because we can see both Venus and Mercury. So if, let's say, these were also present there, then probably we would see these uh, uh, comets with their tails all the time, but that's not the case. Comets show a perceptible glowing tail. Yes, it is known for its tail, while asteroids do not. This is also correct. Asteroids do not show any tail. So 1 and 3. So correct answer, that's why, will be B. that is 1 and 3. Now, after this, we come to almost, you can say, the edge of our solar system, and this is where we have something called as the Kuiper belt. Now, when it comes to the Kuiper belt, this is something which is located beyond Neptune. As you see this is where you have Neptune, and beyond Neptune, you have a very wide region which is called as the Kuiper belt. Now, this is a region where we have a lot of small celestial bodies. A lot of comets are present here. A lot of dwarf planets are present here. A lot of just small dust particles, meteoroids, etc. They're all present here. Now, why such a large number of all these celestial bodies are present here also has a reason. The reason is that now you have come far across from the earth, from the sun, right? So because of that, now the gravitational pull of the sun is little, you can say, weaker as compared to what it has been. So because of this, uh, a lot of smaller celestial bodies, they can exist here. Because if the same celestial bodies, they were present in, let's say, uh, they were present somewhere in the lower, or let's say the inner part of the solar system, then in that case it would have been very difficult for them to survive there, because they would have just been pulled by the sun. But because they are so far away, it makes it easier for them to survive here. And that's why a lot of these celestial bodies, a lot of these smaller celestial bodies, they are found in this Kuiper belt. All right. Now, uh, in this particular scenario, so that's why the Kuiper belt has a lot of small celestial bodies as this region is far away from the sun, and hence gravitational pull of the sun is weak. All right. So that is basically why we see that this is something. Now, in case of Kuiper belt, what we see is that it is located between 30 to 55 astronomical units. So when we say astronomical units, do you know how much is one astronomical unit? Any idea, anyone? How much is one astronomical unit? Correct. It's almost 100, almost, I'm saying almost 150 million kilometers, which basically is the distance between the sun and the earth. The distance between sun and the earth is called as astronomical unit. So that's when now we are saying that we have come how much? Almost 30 to 55 uh, times the distance between the sun and the earth. Then lastly, we have something called as Oort cloud. Now this Oort cloud basically is, you can say, the end. This is the end of the entire solar system, because Oort cloud, you can say in a manner, is a boundary between our solar system and any other solar system. It acts as a boundary because it is a very large space where you have nothing, where you have maybe ice particles and smaller particles like that, a lot of frozen gases. For example, it can have a lot of ices such as water, methane, ethane, carbon monoxide, hydrogen cyanide, etc. All these things are present here. And now we are talking about a distance of 2000 to up to 2 lakh astronomical units. So we are saying that this is an area that can stretch up to 2 lakh times the distance between the sun and the earth. So we have gone so far. So that basically becomes the boundary of this entire solar system. So that is called as Oort cloud, which is a boundary. And then after that, you have other star systems. So for example, you have Alpha Centauri and every other system after that. Now, we have been trying to look across, to observe across, and that is where we have been trying to look for, that we have been trying to look for planets which are closer to how the earth is in composition, if there are chances of finding life on other planets. So all these kind of experiments and all these kind of observation studies are being also done. And that's why this is where we also define something which is called as the Goldilocks zone. This is a question that was asked in your 2015 paper. Any in the outer space. So when it comes to Goldilocks zone, we are talking about a region where the temperatures are neither very low nor very high. So we would say that Goldilocks zone is an area around a star with moderate temperatures. All right. So this is an area around a star with moderate temperatures. So that's why the chances of finding life becomes higher because the temperatures are not very extreme. So for example, let's say when it comes to the earth, earth also lies in the Goldilocks zone because the temperatures on the earth are not very extreme. Even Venus actually lies in the Goldilocks zone. Venus has a very extreme temperature because of its internal reasons, right? But it lies in an area near the sun where the external heat on Venus is not very high. Sorry. So that's why even you can say that Venus also lies in the Goldilocks zone, but unfortunately, because of the internal reasons, it can't sustain life. So that is how we define Goldilocks zone, an area around any star which has moderate temperature. All right. So this basically brings us to the end of the first part of our discussion about the universe and the various aspects of universe and the celestial bodies. If you have any doubts, if you have any questions, please let me know. Let's have a discussion first and then we shall move forward. Zone where water is available in liquid form. Yes, Gavit, you can say that. And that's mainly because of moderate temperatures. Please explain again Oort cloud. So in case of Oort cloud, what we are basically saying is that this is an area which in a manner marks the end of a solar system. And this is an area where you have a lot of frozen gases, a lot of frozen material because the temperatures are very, very, very low. So that's why water in its ice form or other gases like ammonia or carbon dioxide or cyanides, etc., in their frozen form, and that demarcates in a manner the boundary of any solar system and separates all the gravitational and other effects of one star from the other, meaning that you can say that in a manner this is something like this, that it is very bulged out at the equator, all right, very bulged out at the equator and little flat at the poles. So that's why the difference between the diameters of its polar diameters and the equatorial diameters is very high, and that's why we say that it's like a flatter planet. How weak gravitational force leads to the presence of small celestial bodies in Kuiper belt. So basically what happens is because the gravitational force is weak, that's why they can remain there. They have very small mass. So if let's say a small mass body, if it was near the sun, it will quickly be just uh, pulled by the sun because of the gravitational effect of the sun. It will just be pulled by the sun. As it is farther away, it can at least have its existence because now it will have an evened out gravitational effect. So that's why it will not be simply falling towards the sun, and instead it can remain there. expanding. So that's why it's a rough estimate that this could be what it is. System is where it might have collided with some other uh, planet or maybe some other celestial body. It might have changed its direction. The gases on Saturn and Jupiter. So largely we see that hydrogen and helium are the gases which are present mostly on all these uh, gas giants or all these gaseous planets that we have. So most importantly, you can say that these are hydrogen and helium. So for example, let's say in case of Saturn, it's almost 75% hydrogen and almost 25% rest remaining helium. Oort cloud. For that, reasons can be internal, reasons can be external, but yes, uh, there is nothing that is forever. That goes as a rule. Dart mission is also related to an asteroid mission. It was in the news also last year and this year as well. You can say millions of solar systems that are present in our galaxy. Like Earth, Saturn can be a geoid shape. Yes, it is a geoid shape. That's correct. And but it's a much flatter geoid shape as compared to the Earth. Meteorites itself, but rather when they fell, they released a lot of dust into the air. It was like an explosion that is happening because of the impact that they had on the Earth, and that covered the atmosphere. That would have covered the atmosphere. Comets have tails like shooting stars. Yes, in a manner you can say that, but they will look like a passing by star. Whereas asteroids are smaller, just 500 meters in their diameter. Then, apart from that, comets will have a hydrogen cloud. You can say, in a manner, an atmosphere. Whereas in case of asteroids, there is no atmosphere as such. Then, asteroid will be made of largely. It will be composed of a single kind of material. It could be a metal, could be carbon, could be other minerals, etc. And in case of comet, it will be a mixture of metals, minerals, some frozen gases, ice, etc. All these things. And again, comets are much farther. I mean, most of them beyond Neptune, and asteroids between Mars and Jupiter. L1 will discuss this. Just wait. Please upload the detailed timetable for November to December for batch 5. This I'll check with the operations team. I'll pass on your suggestion to them. The spherical shape is because of gravity. That's correct. Clearing the orbit simply means that there should not be anything in the surrounding area that has its own independent orbit around the sun. If there is anything in the surrounding areas, they should be revolving around this planet. They should not have an independent path around the sun. So that is what means by clearing the orbit. Sorry. Why temperature of Uranus is lower than Neptune? It's mainly because of the fact that uh, Neptune has a lot of methane and that can retain some amount of heat. Giant red spot, basically what we are saying is that it's a storm that has been raging on Jupiter, and that's why it looks like a spot when looked from a distance, but it's actually not a spot, but rather uh, a wind that we have observed there. Common, commonly asked by many of you, so that's why I've just picked the common question and I've answered them. I'm not sure if I've missed somebody's question. So why is it not burning? No, methane does not mean that wherever you have methane, it will simply start burning. There is a lot of methane in our atmosphere also. It does not mean that it will all of a sudden it will not start burning on its own. It needs something that will start its combustion. It needs an oxidizer for the burning to happen. And at such low temperatures, burning is not possible. What is Halley's comet? Why is it so popular? Halley's comet has been one of the earliest comets that have been seen, and it has been very visible, and that's why it has been very popular. All right, so let's move on. If there are questions that are unanswered, you can ask during the break as well, and uh, we can again discuss this. All right. Largely important from your prelims perspective. All right. Questions are expected more in your prelims examination from whatever we have discussed until now. Now, the segment that we are entering now, this is a segment that can be equally important for prelims and mains examination. So that's why you have to look at this area from the perspective of both the papers, and we'll also keep on discussing what are the scenarios under which some kind of question in the mains examination could also come. Now, first and foremost, when we are talking about the space technology, we are now going to discuss about what the satellites are and what do we mean by a satellite, how do we launch a satellite, the various aspects of the applications of satellites and the orbits where they are being launched. And there are all these aspects that we are going to discuss now. Now, in case of the space technology, we know that our observations basically about all these things that we discussed, they either can be based on the telescopes that we have, the number of different types of telescopes that we have, or maybe through a satellite or a mission that we launch. So it can either be ground based observation, or it could be space based observation. So when we say ground based observation, we largely are talking about telescopes. We are largely talking about telescopes, deployment of telescopes, and using these telescopes to observe the night sky. Now, this observation, it can be done with the help of a large number of different types of telescopes, but there are two telescopes which are the most common and the most widely used. You have optical telescopes and radio telescopes. So, optical and the radio telescopes, these are the two most widely used telescopes. Now, in case of optical and radio, just try to understand what do we mean and how do they take their observations. So first one that we have here is an optical telescope. Now, in case of optical telescope, it is called so because it uses the visible part of the electromagnetic spectrum. The images that we get from an optical telescope will be similar to the images that we basically can also observe. How we perceive the world, how our eyes would see a planet, in a very similar fashion, an optical telescope will also provide us with the images of any given planet. So that is basically how the things work in case of optical telescopes. So here also you just have to understand that it uses the visible part of the electromagnetic spectrum. Now, in case of optical telescopes, we see that optical telescopes become the most popular of all the telescopes. And that mainly happens because of the fact that these optical telescopes, these optical telescopes, they basically will give us the same image as we can see the world. So that's why they are popular, because the images that you're getting is how you actually would also see something. So, and in case of India, we see that there are couple of telescopes which are very important for India. There is one which is located at Devsthal in Uttarakhand. There is one which is located at Hanle in Ladakh, and then one that we have in the Javri Hills in Tamil Nadu. So these are the three optical telescopes that India has. Now, when it comes to these three optical telescopes, out of these, the one that we have at Hanle, it is particularly very popular and very important for India as well. And Hanle is the place where we are also constructing the Dark Sky Reserve. Dark Sky Reserve. Have you heard of this? This was also in the news mostly last year. It was also in the news. Dark Sky Reserve, that we are building something called as a Dark Sky Reserve. Now, this Dark Sky Reserve is being built in Hanle. What is the purpose? The purpose is watching the night sky, stargazing. So, when it comes to Hanle, Hanle is a very beautifully placed location. When it comes to especially looking at the night sky, the kind of view that you would have from Hanle is unimaginable, to say the least, because of certain reasons. First of all, it is in Ladakh, a cold desert area. Cold desert meaning, desert simply meaning that there is no rainfall or very, very little rainfall. The rainfall can be as less as just 2 or 3 days in the entire year. Just 2 or 3 days in the entire year in case of Hanle. So almost no rainfall means no clouds, means very clear picture of the night sky. That's the first reason. Second reason is that it's a very off location. All right. It's very far away from any populated area. For example, even the Leh city, it's almost, I think, 200 kilometers away from Leh city. So it's an area which is a very remote area. All right. Very remote area. The conditions here are very harsh. The temperatures can go as low as -30, -40 degrees Celsius at times. So at least up to -25 to -30 degrees Celsius. So temperatures will be very low. Water availability is almost negligible because there's no rainfall, there's no source of water, so almost no water, almost no rainfall. uh, Temperature is very, very low, very harsh conditions. Oxygen is very thin. So that's why population wise it has almost no population. And even electricity supply there is also not present. I mean, there is no thermal electricity or any other source of electricity like that. No, obviously no hydroelectricity power plant nearby. So they rely completely on solar energy. So so light pollution also is almost negligible, air pollution almost negligible. So because of all these factors, climatic factors and other external factors, it becomes a very beautiful place to look at the night sky. And that is why a dark sky reserve is being uh, built here. So dark sky reserve basically meaning that this is where you can get a very clear picture of the night sky. So that's the reason why we are trying to basically promote something also called as astro tourism at times, right? So we are trying to promote astro tourism, and it's really beautiful. I mean, I have been there. I've been to Hanle, and this picture that you see right here, this is a photo that I have taken. It's copyright me. So, and this clear picture that you see, bright sunlight that you see, the temperature here while uh, being such a bright sunlight, the temperature was almost -15 degrees Celsius, and the night temperatures were lesser than -20 degrees Celsius. So very harsh conditions. I'd been there in the month of, I think, November and sometime, uh, and I went inside this telescope also. As a visitor, I went there. They showed me around the mirrors and the lenses, etc., that they have there. So, and I understood why all these things. Why I can tell you, because I've seen it upfront and I understand how the things are. Even transport, there's no public transport available. There is just one bus that goes to Hanle from Leh. That's on Saturday. So every Saturday one bus goes there, and every Sunday that bus comes back. So there's only one bus in a week. So it's not that you have very easy availability of public transport. And if you want to take private cabs and private taxis, they can charge you a lot, and it's not easy for everyone to just go there. So that's why it becomes very remote area, and it's a wonderful area. There was even no telephone network, I mean no mobile phone network also. So I was at peace, you can say, for a couple of days. So that's a wonderful place to be in. I mean, if at all you are interested, the view of the night sky is nothing that you can imagine. That even if you, let's say, are living at a far off area, you might have been able to see a lot of stars in the sky. But even then, the entire Milky Way galaxy will be visible from there. You can just Google some of the pictures and you'll understand what I'm talking about. I could not take the pictures because I did not have a good camera. Otherwise, I probably could have shown you that photograph as well. So this is basically about optical telescopes. Then we also have radio telescopes. And there are two important radio telescopes that India has, one located in Pune in Maharashtra, and there's another one again at Ooty in Tamil Nadu. So these are the radio telescopes. Now, radio telescopes will capture the radio waves. Now, obviously, we cannot see the radio waves. We cannot observe the radio waves. For example, our mobile phones also work on radio waves, but you do not see waves around, or you cannot really observe the radio waves. But a lot of communication can be based upon radio waves. And same is happening here as well, that we are basing our observations on the radio waves. Now, why radio waves? Also because radio waves are long waves. Why it matters, we'll discuss that later. I'm not going to discuss this now. When we go to IT and communication chapter, that is where we'll discuss the importance of long waves. All right. So radio waves are long waves, and that's why it becomes the second, you can say, most popular option after the optical telescopes. Now, in case of these telescopes, if you see the difference in observation, this is an image that has been taken by a radio telescope. This is a picture taken by radio telescope, and this is a picture that has been taken by an optical telescope. So as you can see, the second picture is the one that is closer to how we would observe Jupiter if we see Jupiter, right? And the first picture, if you see, that's the image taken by a radio telescope. So that's very different, right? That's not how you look at Jupiter. That's not how our eyes see Jupiter when we see them, if at all we see them, right? So that's basically the difference between a radio and an optical telescope. So these are parts of, you can say, ground based observation, or there are other telescopes as well. For example, there are infrared telescopes. For example, the very famous James Webb. James Webb Space Telescope is an infrared telescope. Similarly, there are X-ray telescopes as well. Our own AstroSat was based on X-rays. So in this manner, we see that there are various different types of all these telescopes. Now, coming to our most important discussion, and this is about how we launch a satellite. Now, for launching the satellite, we first and foremost, what we need is that the object should be able to stay in the orbit. Because if we are launching a satellite, the satellite will be in an orbit, right? They'll have to be in an orbit. And for them to be in an orbit, we'll see that certain laws of physics have to apply on them. And whenever we plan something, whenever we design something, we design it on the basis of all these laws of physics. And here the most important law that works here is the first law of motion, what we also popularly call as Newton's first law. So what does Newton's first law say? That an object at rest will remain at rest, an object in uniform motion will remain in uniform motion unless acted upon by an external force, right? The law of inertia, that object at rest will remain at rest unless acted upon by an external force, correct? So this is what we say about Newton's first law. Now, this Newton's first law is something that will be applicable on all these satellites that we launch into space. All right, all the satellites that we launch into space, Newton's first law will be applicable there. Now, how exactly it is applicable, just try to understand this. And this is something which is, you can say in a manner, a basic tug of war that we have uh, here. Look at this. So first and foremost, what we see is that, let's say this is the earth, this is the earth, and then let's say this is the satellite. Now what we want is that the satellite should remain in its orbit. So for something to remain in its orbit, all the forces there should be balanced. Just take this example. Let's say you have a surface, and on this surface you have a block that is kept there. So this block, let's say you start to push the block in a direction. So when you push the block, when you provide it certain amount of force, it will start moving in a certain direction, in the forward direction. All right. So let's say I start putting force in this direction, so it starts going in that direction. Let's say I have put a 10 Newton force here. Then suppose that somebody else also comes from the other end, and they also start pushing it from that end, and they are also putting a 10 Newton force on it. Then what happens? The force from both the sides are balanced. So then in that case, this box will remain where it is. So something similar needs to happen for a satellite as well. That wherever the satellite is, all the forces acting on that satellite from all the ends should be zero. So now there is one force which is constant, which is the gravity of the earth. So earth with its own gravitational force will keep on pulling the satellite towards itself. Sorry. So we need to provide a counter force. Correct. We need to provide a counter force which will act in the opposite direction. We need to provide a force opposite to the force that is the pull of the gravity of the earth. So how do we do that? By providing a thrust, by launching that satellite. So when we launch a rocket, when we launch this satellite, we provide it a lot of energy. Correct. We'll provide it a lot of energy. We basically provide it a lot of thrust so that it can move away from the earth against the gravity. Correct. Against the gravitational force, we are providing a thrust. So that motion basically provides the opposite force, and we would provide it as much force as it is required, so that at a certain height it should have uh, zero forces applicable on it. So that is basically what we'll have to do. So ultimately what we need to do is we have to balance the forces. We have to balance the forces. And how do we balance the forces? On one end you have something called as the centripetal force. Centripetal force, which has to be equal to something called as the centrifugal force. So here, what do we mean by these forces? Centripetal force is the force acting towards the center. Force acting towards the center. In this case, it is gravity, right? In this case, it is gravity. The gravity of the earth with which the earth is pulling this force. And on the other hand, you have centrifugal force, which is the force acting away from the center. The force acting away from the center. And this is mainly, how exactly are we providing it? This is being provided with the help of the motion. This is because of the satellite motion. So this is how we will try to balance these two forces. And wherever we have been able to balance the forces, that is where it will start taking the orbit. So the calculations that we will do, the force that we will provide, will be based upon what is the height at which we want to place the satellite. So for example, if we want to place the satellite at 500 kilometers, then we will provide as much force as it is required, so that at 500 kilometers the forces are balanced. If let's say we have to send it to 35,000 kilometers, then we will provide it the force in a manner that at 35,000 kilometers the forces should be balanced. But the basic principle is this: the basic principle of launching a satellite or keeping the satellite in a given orbit is that the forces acting on a given satellite should be balanced. Wherever we want it to be balanced, it should be balanced at that point. So that is basically how this is, you can say, the basic principle. Of course, things are much more complex than whatever we are discussing here. uh, Rocket science is called as rocket science for a reason, because there are a lot of other things and there are other parameters also that come into the account. So for example, there is nothing which is completely circular or completely spherical. So there is an assumption that everything is circular and spherical, which makes our job easier, but that's not the case. And that also changes everything. Then there is air resistance in our atmosphere, that also changes the thing. You're losing fuel, you are losing the weight of the satellite, that also changes the things. So there are n number of factors that come in the picture in the real scenario. But the basic principle is balancing the forces. The basic principle is wherever you are able to balance the forces, you will be able to keep the satellite there. So if I want a satellite at 500 kilometers from the earth, then at 500 kilometers all the forces acting on this satellite should be balanced, so it will always remain in 500 kilometers orbit. So it will keep on orbiting at 500 kilometers. So just remember, the key word is balancing the forces. Balancing the forces. There's one question that was asked in your paper. I would say it's kind of a difficult question. Exactly, do we arrive at this answer? The question says the artificial satellite orbiting around the Earth does not fall down. This is so because the attraction of the Earth, first, is does not exist at such height. That's completely wrong. Gravitational force of the Earth will exist. Just imagine you have a moon which is way farther away and it is still being attracted by the gravity of the earth. So something which is a satellite which is much nearer to the earth, there is no chance that the attraction of the earth does not exist. So A is definitely wrong. Second is neutralized by the attraction of the moon. That is also incorrect. Moon again is farther away, plus moon is very small, so its gravitational pull is also very small. So that's why B cannot be the answer. Now comes the real problem between C and D. C says provides the necessary speed for its steady motion, and D says provides the necessary acceleration for its motion. All right. So basically, you can say here we are talking about between speed and acceleration. That whether it is about speed or whether it is about acceleration. Why acceleration is correct? Just think of something very simple. What is the formula for force? Force is equal to mass into acceleration. I'm sure that you have heard of that. You might have forgotten it, but I'm sure that you've heard of it. So force is equal to mass into acceleration. Now mass is something that we know of, correct? Mass is fixed. So we are not bothered about mass. What are we bothered about? Acceleration. How do we provide the required force? By providing that necessary acceleration while we are launching the satellite, because it's about balancing the forces. Why not speed? Because the speed will keep on changing with its direction. It's not about speed, but rather it is about velocity. It is more about velocity, meaning just not the speed, but also speed and the direction in which the speed is being provided. So basically that is where we are coming from, and that's why providing the necessary acceleration for the motion would be the correct choice here. But as I said, that it's not an easy question to answer. It definitely makes it very difficult. uh, but they actually have asked this question in your paper. All right. So Next, coming to the understanding of the orbits, I think we should, it's a bigger topic, so maybe we can take a break here itself. Can we for a break will not be a good idea. Back by 6:15. At that point of time, whatever dynamics could basically happen, they all happened and they then became static. So at that point of time, all the smaller planets, because they are smaller, they have lesser gravity, they could sustain lesser number of celestial bodies around them. And then the bigger planets, they basically have more numbers. So for example, the smallest two planets you have, Venus and Mercury, it became very difficult for them to sustain a moon around them, with this large sun also being so near. And that's why Venus and Mercury, they do not have any moon. Earth has one, and Mars has two. And then after that, you have all the bigger planets which could sustain more number of moons with their size, and also being farther away from the sun. Orbit is not near to its orbit. Yes, absolutely correct. That's the case. How centrifugal force acts on satellites to balance its motion. So basically, what we are saying is centrifugal force is the force that we are providing. The thrust with which you launch a rocket, that launching of the rocket itself is the centrifugal force. Can you please give a summary on Osiris Rex and asteroid Bennu? See, Osiris Rex basically is an asteroid collect sample mission, and when it comes to Osiris, so this term Osiris itself is an acronym. Regolith Explorer. So it basically is an acronym for this entire work that it has to do. So when we say regolith explorer, regolith means the uppermost part of the soil. So because it is going to collect those samples from this particular asteroid, that's why it is a regolith explorer, and it will be able to give us a basic understanding of the origin of the solar system itself, or maybe about the asteroids, because it's a carbon rich asteroid. And we know that Earth also has a lot of carbon, other planets also have a lot of carbon. So that might give us an insight about some of these things. And so that's the origin of this solar system. Spectral interpretation, meaning understanding of everything that is present there, plus resource identification, RI. So the resources that are present, the things that are there. And security, S, meaning we also need to identify how this asteroid is traveling, or is there a possibility that these kind of asteroids might hit the Earth someday. So from that perspective, we are talking about the security aspect, and that's why this name Osiris Rex has been given to this mission. And it went to Bennu. Bennu basically is what? Is an asteroid which has large amount of carbon. Right? It has lots of carbon in it, and it was chosen mainly because it is very similar in its composition compared to many of the planets. Neptune and Pluto. Between Neptune and Pluto, it does happen that Pluto sometimes comes inside Neptune. So it does happen. How the centrifugal force is provided in revolving satellite. So basically, the revolution of the satellite will be uh, calculated. All right, it's a calculation that we do before we launch the satellite itself. The circular motion, basically, if you know the formula for circular motion, mv square by r, so that will be calculated first. The velocity will be calculated first, and based on that, we will provide it the angular velocity as well. Can we say that collision of stars as a natural calamity? It's not a calamity for us. It's just a natural phenomena, we would say, because it's not causing any harm. It's not doing anything to us. So that's why calamity is a term that we use in negative sense. So we should not say that it's a calamity. Can you please repeat why D is the correct option in the last question? So here what we are saying is that we basically have to balance the forces. And balancing, when you are trying to calculate the force, you already know the mass, right? Mass is what? The mass of the satellite itself. So we designed the satellite, we know how much the satellite weighs. So mass is not the problem for us. We need to calculate the acceleration. We need to provide it the required acceleration so that it can take the required motion. The satellites rotating in clockwise or counterclockwise direction, we can basically design whatever we want. So there is nothing that is fixed. We try to just gain from the motion, but we'll discuss that later, how exactly we do that. Majority of questions in science and tech are from current affairs. Not exactly correct. Many of them are the static areas of the current affairs as well. So it's not that it's all current affairs questions. Is there any other star which has planets? Multiple, many of them. There are many, many stars which have planets around them. How satellites move same speed as Earth, we'll discuss that later. It's a part of our discussion that we'll do most probably tomorrow. All right. So let's move on. Now, looking at the understanding of the orbits, there are two scientists who become very, very crucial when it comes to our understanding of the orbits. We have Kepler and we have Newton. Now, Kepler was somebody who gave three laws of planetary motion. He basically had given three laws that govern how exactly the motion of planets around the sun happen. So he was the one who observed something, and based on that, he had given three laws. And the same three laws for Kepler, basically, what he said is that all these three laws are applicable on planets which move around the sun. But then came Newton, and Newton gave something called as universal law of gravitation. And then he basically said that all these three laws, they are not only applicable on the on the planets which are moving around the sun, but rather these three laws will be applicable on anything that is moving around anything. So that's why the same three laws which are applicable on the planets revolving around the sun, the same three laws will also be applicable on the satellites that we now launch. And we'll see that the same three laws are applicable there as well. So let's try to understand this first, that what are these three laws of planetary motion. So the three laws that were given by Kepler, the first law says that all planets move in elliptical orbits with sun situated at one of the foci of the ellipse. We'll discuss what exactly it means. Second one says planets sweep out equal areas in equal times. And third one says orbital period squared is proportional to the size of semi-major axis cubed. Seems very technical and difficult, but it's not actually the case. We'll discuss what exactly these mean. So first one says that planets are in orbits with ellipse. Planets orbit in ellipses with sun at one focus. Now, what we basically mean is that first and foremost, what is an ellipse? Ellipse is this kind of a shape, right? This kind of a shape is called as ellipse. So any ellipse will basically have major axis and minor axis. These two, there is a big axis and a small axis. So big one is called as the major axis, the small one is called as the minor axis. And there are 2 points which are situated here. They are called as the focus. All right, these will be called as the focus. Now the same when it comes to this ellipse, there can be multiple types of ellipse. It can be a very elongated ellipse like this, or even a perfect circle. Circle is also an ellipse, just that these two axes that we were talking about, these axes now become the diameter. The axis basically become the diameter. So that's why circle is a special case of an ellipse. So even circle is an ellipse. All right. So these are various different types of ellipses. So now what we are saying is that planets, they basically are moving in an elliptical orbit. All right. They have an elliptical orbit, and sun is situated at one of the foci of this ellipse. So basically sun is situated here, and all the planets that we have, the planets basically will be having a orbit like this. So you have a planet here and you have the sun here like this. So this is basically what this first law simply says, that he had simply observed that whatever planets he sees, all these planets have an elliptical orbit. The shape of the ellipse could be different, but just that it's an elliptical orbit. That became the first law. Then the second law. The second law says that planets, they sweep out equal areas in equal time. Now, what it simply means is that if you look at this picture that you have a 10 days time period here, and you have a 10 days time period here as well. All right. You have a 10-day time period in both the cases. So because the time is same, 10 days in both the cases, because the time is same, the area will be also same. The area that it is sweeping will also be same. So this is basically what we mean by equal area in equal time. All right, equal areas in equal time. This is basically what we mean by the second law. So now, how did he come to a conclusion that this is the case? Equal areas in equal time. What he observed is that when the planets, they are closer to the sun, they move faster, and when they are away from the sun, they are moving slower. If you see this, when the planet is close to the sun, in 10 days it has covered so much of distance, right? And when it is away from the sun, it has covered a very small distance, as you can see this. So the planets, when they are nearer, they are faster. When the same planets are away, they are slower. This is what the second law simply says, and this is where it comes from. All right. So that's why planets, they move faster when they are closer to the central object, which is basically the sun in this case, and they move slower when they are farther away from the central object. So this was the observation. Based on this observation, when he kept on doing the further calculations, he came to a conclusion that in equal times, equal areas are being covered. All right, equal areas are being covered in equal amount of time. So that is something that became the second law. This became the second law. And then there was the third law, which says that the orbital period squared is proportional to the size of semi-major axis cubed. Now, this seems very technical, but actually it's saying a very simple thing. What it simply is saying is that if there is a planet which is close to the sun, all right, when a planet is close to the sun, it takes less time to complete one revolution. When a planet is away from the sun, it will take more time to cover one revolution. That's it. This is what the third law is. So, for example, let's say when you talk about the Earth, Earth takes 365 days to cover one revolution. When you compare Earth to Pluto, Pluto takes how much? Pluto takes 238 years to cover one revolution. So on one day, one hand we have on the one hand we have Earth that takes 1 year to complete one revolution. On the other hand, you have Pluto that takes 238 years to complete one revolution. Earth is near, Pluto is far. This is what the third law says. That if you are near the sun, you take less time to complete one revolution. If you are away from the sun, you will take more time to complete one revolution. That's it. This is the third law. So that's why, in a manner, and all these were based on observations. All these laws were based on observations, and and also interestingly so, the observations were not made by Kepler. All these observations were noted by the teacher of Kepler, the mentor of Kepler. he had made a lot of observations, and when Kepler was reading all these observations, he was the one who saw a pattern, and then based on those patterns he kept on observing further for the next few years, and then ultimately he came to a conclusion. So the laws were given by Kepler, but actually uh, the observations initially were noted by the teacher, or the mentor of Kepler. So that is where the three laws came from. And then after that, Newton came, and Newton gave a universal law of gravitation, and that's why then he said that all these laws which are applicable for all these planets revolving around the sun, they will be applicable everywhere. Wherever you have one body revolving around the other, it will be applicable. And that's why later on, when we started making satellites and designing satellites and sending them to orbits, the same three laws come into existence while launching the satellite as well. So in this basically scenario, we see all these things. So in a manner, you'll see that second and the third law are also very close to one another. Almost, you can say third law can be seen as a result of the second law, that you can derive third law from the second law itself, correct? That because you are already saying that when the planet is uh, near the sun, it is faster, and when it is away from the sun, it is slower. So obviously it is faster, it will take less time, and anyway it is covering lesser distance, so it will take less time. So third law basically comes from all these conclusions. Now coming to the types of orbits. Now there are multiple different types of orbits that will be mentioned in your newspapers. So for example, sun synchronous orbit, geosynchronous orbit, geostationary orbit, polar orbit, equatorial orbit, all these are terms that are very often seen in the newspapers. So that's why just understand basically what exactly uh, we mean by all these orbits. So in simple terms, we can classify the orbits into three categories. First category is low earth orbit, second is medium earth orbit, and the third one is high earth orbit. Low earth orbit are all the orbits between 180 kilometers to up to 2000 kilometers. All right, so in this range, whenever you have an orbit, we say that it is a low earth orbit. All right, then medium earth orbit will start from 2000 kilometers and goes up to 35,786 kilometers, and high earth orbit is at or above 35,786 kilometers. Now, why such a specific number? 35,786. Why are we not saying 35,000 or 36,000? There is a reason for that. This exact number, 35,786 kilometers, this is the exact number where if you have placed a satellite, the satellite will have an orbit of 24 hours, meaning that it will take 24 hours to complete one revolution around the earth if it is placed at 35,786 kilometers. So that's the basic reason, right? That's the reason why this number. I'm just writing it here at 35,786 kilometers. Orbit period of a satellite revolving around the earth is 24 hours, right? So in 24 hours it will complete one revolution if it has been placed at a height of 35,786 kilometers above the earth. All right, so that is why this so specific number, such a specific number, has been chosen. Now when it comes to all these types of orbits, there are certain factors that we use to determine any orbit. Now just understand this. There are three major factors. The first factor is height. Now why does height matter, and rather how does height matter? Just take this into account. All right, suppose that, suppose you have the earth like this. All right, let's say this is the earth, and then you have 2 points, A and B. Suppose that this is A and this is B. Now if I ask you, if I have to observe the earth, if I have to take pictures of the earth, pictures or videos of the earth, should I go with A or should I go with B? Where should I place my satellite if I have to take the pictures and videos of the earth? Should I take the pictures and videos from A or should I take the pictures and videos from B? Let me take a very small fun pool with you to understand what you think. Hmm. So it's a very small fight here. 49% of you have said A and 51% of you have said B. The answer actually will be A. Pictures and videos of the earth, if we have to take, will be at A and not B, meaning that we'll try to be as near the earth as possible if we are taking pictures and videos rather than being far. What's the reason? The reason is the HD quality. The quality of the pictures that we'll get from A will be very good as compared to B, because B, I understand where you're coming from. I'm sure that you're thinking of range, that you'll be able to cover a larger area when you are taking from the picture from B, and from A you probably will not be able to cover that large an area, and that's correct. You're correct in thinking that. But when we take the pictures and videos of the earth, when we are observing the earth, we are not bothered about the range of our coverage. We are bothered about the quality of our coverage. So for example, let's say if there is a satellite for disaster management, all right, so it will have to take pictures and videos of the earth to understand the situation at a given area. It will have to take pictures and videos. Now the clarity of the pictures and videos taken from near the earth will be much better as compared to when you are taking it from far away from the earth. So that's why they'll be kept at a height which is much lesser as compared to any other application. All right, so that's why will be near. All right, so just think of your camera, that if you had to take your picture, would you rather keep your camera near you or would you take it from far away just to cover a larger range? You're not bothered about the range, you are bothered about the quality of the image of the picture that you're taking. Same goes for these satellites as well. The satellites also will take a better picture if they're nearer. Understood? That's why height matters. That's why the altitude of the satellite will matter. Similarly, if let's say there's another aspect of communication, there is another aspect of communication. So if it's a communication satellite, then range matters. All right, so here I'm just writing here A because quality matters. All right, and in case of communication, range matters. So that's why B will be better suited. All right, B will be better suited. So that's why we see that this is what we do. That if you have to observe the earth, take pictures and videos, will try to be near the earth. And if you have communication purpose, you need a better range, then in that case, you'll be far away. So this is how basically we will determine the height of the orbit based on that. Then the second factor is eccentricity. Eccentricity simply defines the shape of the orbit. Shape of the orbit, whether it is highly eccentric, whether it is circular orbit. So all these things, and they also matter, and we'll discuss later with examples how exactly eccentricity or the shape matters. We'll discuss that later. Just wait for now. Then the third is inclination. Inclination from the equator, whether it is at the equator. So then in that case, you'll call it as an equatorial orbit. If it is highly inclined, you will call it as a polar orbit. So inclination will determine whether it is an equatorial orbit or polar orbit. So this also basically will be determined based on the application. Determined based on application. So that's why equatorial or polar, that also matters, and we'll discuss that again as we move on. You'll automatically understand uh, how inclination matters and how inclination is determined. So these three factors, understand that: height, shape, and inclination. These three factors become very crucial in determining what kind of satellite is to be placed where. All right. Now, based on that, we have the different types of orbits. The first one is the low Earth orbit. Now, what we discussed about the low Earth orbit is that low Earth orbit is placed between 180 kilometers to up to 2000 kilometers, right? 180 kilometers to 2000 kilometers. I'm just writing the basics here. So, height is 180 to up to 2000 kilometers, correct? Then comes application. So application, because it is near the earth, what is the application? Observing the earth. So application is earth observation. Earth observation, something that we also call as remote sensing. This is also called as remote sensing, because we are remotely trying to sense the earth or remotely observing the earth, and that's why remote sensing is another name that is used here. So application is this. Then, so we know the height, we know the application. Then when it comes to the orbital period, the orbit period is just of 1.5 to 2 hours. So meaning that in 1.5 to 2 hours, it will complete one revolution. So it will be very quick around the earth, right? It will be very quick, because at 35,000 kilometers, we see that it becomes 24 hours. At almost 500, 600 kilometers, in most of the cases, they'll be placed at, it will be around 1.5 to 2 hours time. Then one more thing, when it comes to the low Earth orbit, we see that these are lightweight satellite. These are lightweight satellites. Also, the launcher that we use here, and we'll discuss about launchers later. Launcher that we use here is called as PSLV. You might have heard the term PSLV, which is Polar Satellite Launch Vehicle. All right. So Polar Satellite Launch Vehicle is the primary launcher that we have for the low Earth orbits. Uh, then one more thing, their life cycle. The life cycle of these satellites is largely between 3 to 5 years. All right. So this is basically how we are making the use of all these. So just know these points and why these points are important. See, many a times when the questions come, even if it's a current affairs question, so let's say they ask you a question based on any recent launch, whatever happened, let's say in the last 1 year or so. Now, based on all these things, if you can link all these pieces of information together, even without knowing that current affairs news, you will still be able to answer the question. You'll still be able to answer the question. I'll tell you how. So, for example, there was one question that was asked on astrosat. All right, astrosat. Now, so lightweight satellites. So, when I say lightweight satellites, this is less than 1500 kg. Less than 1500 kg. All right. So that is what is lightweight satellite. So less than 1500 kg. Now the question that was asked on astrosat, one of the statements, so what we know about astrosat was that it was launched using a PSLV. So if PSLV has been used, it cannot be a heavy satellite, correct? Can't be a heavy satellite. One of the statements that was given for Astrosat was that it is a 2000 kg satellite. It can't be a 2000 kg satellite because PSLV was used. So even if you don't know what was the exact amount of or exact weight of Astrosat, even then you can answer that question just by knowing how to relate all these pieces of information. That when we say low earth orbit means height being 180 kilometers to 2000 kilometers. Largely it is between 500 to 700 kilometers only, but less than 2000 kilometers. Application, what is application? We want to be near to take the pictures and videos, so the application is earth observation, or also something called as remote sensing. So that's why these satellites are also called as remote sensing satellites. Then orbital period is between 1.5 to 2 hours, because they are very quick, because they are so near, so that's why they will be quick. They are lightweight satellites, meaning that they weigh less than 1500 kg. You will see that in most of the cases they don't even weigh beyond 500 to 600 kg. In most of the cases they will be lesser than 600 kg. Forget about 1500 kg. PSLV will be the primary launcher. So for lightweight satellites we will use PSLVs, and that's why you'll see that for many missions wherever we have used PSLVs, they all have been lightweight satellites, whether it is normal Earth observation satellites, or even Mangalyaan mission, or Astrosat mission, or Aditya L1 mission that we just launched. In all these cases, these are lightweight satellites. So even if Aditya L1 has been launched with the help of PSLV, it simply means that it cannot be a very heavy satellite. It cannot be a very heavy satellite. So that's why just remember all these points together, so that you can relate all these information, and even if you don't remember current affairs, you can still apply this knowledge and answer that question. And you will see that it really works. Whenever such kind of a question has come, it really works if you just know this. Now there are two types of there are two types of low earth orbits: polar orbits and sun synchronous orbit. Now in case of a sun synchronous orbit also, we say that it's a special case. It's a special case of polar orbit, right? It is a special case of polar orbit. So it's not that it's different, it's a special type of polar orbit. It's a special type of polar orbit. Now in this case, just understand, when we say polar means what? That it will be synchronized with the poles of the earth. So we know that there are poles of the earth, so they will be revolving like this. All right, they will be revolving like this at the poles of the earth, right? Or along the poles of the earth. Sun synchronous orbit gets its name because it is synchronized with the local solar time of a place. So it gets its name because it is synchronized with the local solar time of a place. Now, what do we mean when we say synchronized with the local solar time of a place? What it means is that, let's say if this kind of a satellite is overhead Delhi at 10 a.m. in the morning, then every day at 10 a.m. it will be overhead Delhi. Tomorrow again 10 a.m., day after tomorrow again 10 a.m., again 10 a.m. So every day at 10 a.m. it will be overhead Delhi. Now there's a question. We are saying that it completes one revolution in 1.5 to 2 hours. So why is it not that it is again overhead Delhi at 12 o'clock? Why that's not the case? Can you think of this scenario? That why is it not that it is back over Delhi just in 2 hours? Why is it taking so long? Yes, Pravalika, you are correct. Namrata, correct. Akansha, correct. Lakshmi, correct. Siva, correct. Samson, correct. Wonderful. So many of you have given the correct answer. So The simple answer is the Earth is also rotating. So by the time it comes back to the same latitude, it does not come back to the same longitude because the Earth has rotated. Correct? This is what this picture is trying to signify, that the next time when it comes back, it does not come back to the same place because the Earth has moved, Earth has rotated. So that's why it will be synchronized in a manner that 24 hours later it will be back at the same place where it was. So that's why sun synchronous orbit. That's why it is called as the sun synchronous orbit, because it is synchronized with the local solar time of a place, that it will be overhead at the same time over and over again every day. And that is why it is called as sun synchronous orbit. Now the question is, why to synchronize? Why to take so much pain that it is being synchronized? The reason is that it helps us get a better data, that you are getting the data every day at 10 a.m. So you get a consistency in data. All right. This basically helps with consistency of data. Helps with the consistency of data. All right. So that is why sun synchronous orbit will be preferred. And that's why this is sometimes also called as SSPO. When you look at the newspapers, you'll see that they'll say that the satellite has been launched to SSPO. So SSPO means sun synchronous polar orbit, because as I told you, it's a special type of polar orbit. That's why the terms SSPO is used many a times, or will also be used. So sun synchronous polar orbit, that's why SSPO. So this is low Earth orbit, which will largely be used for Earth observation, which is also called as remote sensing. Also called as remote sensing. So that is how we will use the Earth observation satellites. So all these are the various ways in which we can make the use of Earth observation satellite. All these basically I've taken the list directly from ISRO. ISRO website has listed out that these are the ways in which Earth observation satellites are used. So basically anything that needs to observe the Earth, take the pictures and the videos of the Earth, will be called as an Earth observation or a remote sensing satellite. So there are multiple examples: Cartosat, OceanSat, ResourceSat. Generally, the nomenclature goes like this: that you write the name of the application plus SAT. This is how the naming of the Earth observation satellites is done in most of the cases. In case of the Indian satellites, then after that we have the medium Earth orbit. Now, in case of medium Earth orbit, again there are two types of orbit. One called as semi-synchronous orbit. Now, semi-synchronous orbit basically is called so because it has an orbit period of 12 hours. The orbit period in this particular case is of 12 hours. All right. So, semi-synchronous. That's why semi-synchronous, because it completes two revolutions in a day. One revolution in 12 hours, two revolutions in a day, it will be able to cover. Now, this is a satellite, or sorry, this is an orbit which is basically used by GPS. This is used by GPS, and this is placed at a height of 20,200 kilometers. 20,200 kilometers. So this is the semi-synchronous orbit, largely used by GPS. Largely used by GPS, but some of the other navigation systems, like the European navigation system also, or the Zenith that belongs to Japan, in these cases also we see that they use the medium Earth orbit. So semi-synchronous orbit is used in that sense. The second orbit, and which is a very interesting orbit, is Molniya orbit. Now, this picture that you see right here, this picture is of Molniya orbit. Now, Molniya orbit is an orbit that was specifically designed by Russia, or in a manner you can say that this was invented by Russia. This is an orbit that was invented by Russia, or rather USSR at that point of time. This was invented by USSR. Now, this particular cases, in this particular case, Molny orbit, why exactly did they have to invent this orbit? For a very simple reason. Generally, when we place any communication satellites generally are placed on the equator. All right, they will be an equatorial orbit. Now, what happens is that if let's say they have a range like this, then they are missing out on the polar areas, right? They are missing out on the polar areas, and we know that Russia has a large landmass in the polar areas. So, an equatorial communication satellite does not work for Russia. So that's why they thought that they'll have to design their own orbit so that they can take care of their communication needs. So if you see this, what's happening here is that it's a highly eccentric orbit, right? Very elongated orbit. So second law applies here. Second law will apply how? That when it is in the southern hemisphere, it will move very quick, and then in the northern hemisphere, it will take its time. Correct. So it will spend a lot of time in the northern hemisphere and a very small amount of time in the southern hemisphere. Application of the second law, that when you are near the central object, you are faster. When you are away from the central object, you are slower. So they invented by USSR for its communication needs. All right. So that's why Molny orbit was invented. Now, there's another side to this story. This was the Cold War era. Uh, and in the Cold War era, we know that there were two poles. One was USSR and one was USA. So obviously, whatever USSR said, USA never believed it. And whatever USA also said, USSR never believed it. So when USSR invented this orbit, uh, when they invented this orbit and they said that we need this orbit for our communication needs, USA had a different story. USA said that these people are lying. They're not going to use it for their communication needs. They're actually going to use it to spy on us, because this is a satellite orbit that we cannot track. It's a new orbit altogether. So that's why we can't track this orbit, and hence they can very easily place their spy satellites over USA with the help of Molny orbit. This is the USA side of story. So whether this is correct or whether it is not correct, we never know, and we would never know. So these are just two sides of the stories. So one side of story is that they needed it for communication purposes. The other side of the story says that they probably would have used their spy satellites in the same orbit. So, but we would go with the official information and not the conjecture. So this is basically what they said about the Molny orbit. Now, GPS, as I just told you, that GPS basically uses the semi-synchronous orbit, and semi-synchronous orbit, it can use a constellation of up to 34 satellites. Let me write up to 34 satellites, because it's not always 34. Sometimes it's 30, sometimes it is 32, but up to 34 satellites can be used in this GPS system. As I told you, that it is placed at approximately 20,200 kilometers above the Earth. Now, in this case of GPS, what we see is that there is one concept that is used here. The concept is called as triangulation. Now, the concept of triangulation basically is that there are three satellites that they use together to look at, or rather identify a certain area or provide the positioning information about a certain location. So this basically is something uh, that GPS does. So that's why triangulation, because a set of three satellites will be used. And while using these three satellites together, they increase the accuracy of the satellite. They increase the accuracy of the GPS. So, because one satellite probably would have not been able to give that much accuracy. That if let's say one satellite covers this area, the second satellite probably covers this area, and the third satellite covers this area. So in this manner, when all the three are used together, then in that case, the accuracy of the information will be very high. So that's why GPS uses this concept called as triangulation. So triangulation is use of three satellites together to provide location or position services of a certain place. All right. So that's where triangulation, that's where triangle is where it is being uh, derived from. So this is what GPS does. Now we also, I'll come back to this question later. Just wait for some time. The third kind of orbit is the high Earth orbit. Now, in case of high Earth orbit, again, let me just give you all the basics. First, the height. Height is how much? 35,786 kilometers. Correct? This is the height. What is the application? Primary application is communication. Primary application is communication, and any type of communication. It can be radio, television, mobile phone, internet, any kind of communication. The application basically for high Earth orbit. Then we see that you have heavier satellites here. Heavier satellites, and these satellites can be 4,000 kilograms or 5,000 or even 6,000, 7,000 kilograms. So they're very bulky. The communication satellites, they're very bulky. So we use another launch vehicle here. The launcher that we use here, is GSLV. All right. The launcher that we use here is GSLV. Then after that, what else? The orbit period, right? Orbit period, we already discussed that when you are at 35,786 kilometers, it will be of 24 hours. So orbit period is of 24 hours. And then the life cycle. The life cycle of this satellite will be higher. It can be up to 15 to 20 years. So on one hand, we discussed that the low Earth orbit satellites, they are functional for like 3 years or maximum of 5 years, whereas the life cycle of a satellite in this scenario can be up to 15 to 20 years. And that is also one of the reasons why we keep communication satellites here, because it's not that we can't keep communication satellite in the low Earth orbit. We can. It's just the problem of range. You increase the number of satellites. Instead of one satellite, use 10 satellites. But then it's not only using 10 satellites, but rather those 10 satellites will be functional for 3 years. And here the same satellites will be functional for 15 years. So 10 into 5. So instead of using one satellite, you will be using 50 satellites to compensate for that one satellite if you are keeping the communication satellite in the low Earth orbit. So it's not cost effective, right? Long story short, it's not cost effective. So that is the reason why it's not that we can't keep communication satellites in the low Earth orbit. We can, and it probably will give us better results. But ultimately, the fact is that it will not be cost effective, and hence we keep it in the in the high Earth orbit. Now, again, in the high Earth orbit, there are two types of orbits. One called as the geosynchronous orbit, or GSO, and the second one called as the geostationary Earth orbit, or GEO. Again, this is also, you can see in a manner, is a special type of GSO. All right. This is a special type of GSO. Now, why are we saying that this is a special type? Just try to understand the basic differences between the two. That what is GSO versus what is GEO. Now we discussed that there are various factors, correct? The first factor that we had discussed was height. So height wise both are same, at or above 35,786 kilometers. Right? So height wise both are same, so no difference here. Then the second factor that we had discussed was eccentricity or the shape. Now this is where there's a difference. Geosynchronous orbit will be elliptical, whereas geostationary orbit will be circular. It will be circular uh, in its shape. So that's the second factor. The third factor that we had discussed was inclination. Now, inclination wise, what we see with geosynchronous orbit is that it can have a small inclination. All right, it can have a small inclination. So you can say, we'll write here small inclination possible. But in case of geostationary orbit, it has 0 degree inclination with the equator. It has a 0 degree inclination with the equator. So in a manner, it lies in the plane of the equator. Now understand something here. In case of geostationary orbit, just look at the column of geostationary orbit. Height is fixed. It is circular. So shape is also fixed. Inclination is 0 degrees. So there cannot be any further variation. So because all these factors are fixed, it's a unique orbit. It's a unique orbit. Whereas in case of geosynchronous orbit, variations are possible. Right? Variations are possible, but in case of geostationary orbit, variations are not possible because all the factors are fixed. So there is only one geostationary orbit, whereas there can be multiple geosynchronous orbit. All right, there are, so let me make it easier. Multiple orbits possible. All right, so on one hand you have multiple orbits possible, on the other hand you just have one unique single orbit. So that's why we are saying that geostationary orbit is a special case of geosynchronous orbit. So this is how it is. So geostationary orbit basically lies on the equator. It lies on the equator, whereas geosynchronous orbit, it can have a small inclination from the equator. Now when we look at all these communication satellites, again there are various ways in which communication satellites can be used. Telecommunication, telemedicine, teleeducation, television, mobile communication, radio communication. In all these cases we can make the use of communication satellites. All right, in all these cases communication satellites can be used, and we have different groups of satellites: the INSAT satellites and the GSAT satellites. Initially when we started launching our satellites, we were using the nomenclature of INSAT satellites, and then after that when we this was the time when we actually could not launch our own satellites. GSLVs were not there, so we used to take the help of France or Russia and get our satellites launched. But then we also developed our own launch vehicle, that was the GSLV, and then we changed the nomenclature of these satellites from INSAT to GSAT. So that's the basic difference. Now, apart from that, we are also using these all these orbits for navigation purposes, and there are two navigation satellites or two brackets of navigation satellites, one called as Gagan, second one called as Navik. So first, to start with, what is Gagan? So there are two ways in which navigation satellites are being used. Now GPS is also a navigation satellite, but GPS uses a medium earth orbit. But in our case, when we are using our satellites, we actually don't use the medium earth orbit. We use a mix of medium earth orbit and a high earth orbit also. How exactly? Let's see that. So first and foremost, we have Gagan. Now, this Gagan, if you see this, it makes the use of the GPS satellites and also makes the use of geostationary satellites. So that's why it is making the use of medium Earth orbit, and it is also making the use of high Earth orbit. It's a you can say a mix of both, and that's why Gagan basically means GPS aided geo augmented navigation. That's why GAGAN, Gagan. Now, this is a system that was jointly implemented by ISRO, or Indian Space Research Organization, and Airports Authority of India. They both collaborated, they came together, and they designed this Gagan system for civil aviation, to provide civil aviation applications. But it's not that it is only applicable or only useful for civil aviation, it can be used for other purposes as well. If we want, we can use it for different purposes. So that's why it can be used in uh, intelligent transportation or maritime highways, railways, surveying, uh, geological applications, geodesy applications. In all these cases, we can make the use of Gagan system, but primarily for civil aviation. Now, why civil aviation? Because we wanted reduction in cost. This will help us in reducing cost, reducing time of flight, and save fuel as well. All right. So that is basically what we want, is we want to reduce the flight path. So if you know, I mean, it may not be required for you, but let's say, if let's say something is flying from Kolkata to Bangalore, all right, then in that case it's not that it takes a straight line path. You will see that it will take a circular approach like this, maybe something like this, or maybe it comes like this. So it will not come in a straight line path. So obviously the total distance that it is traveling is much larger than the actual straight line distance between the two places. And there are reasons for that. One simple reason is also the rotation of the earth. Apart from that, we take into account the landing and the takeoff, and all the avionics have to be taken into account. So that's why it takes a longer route. So we are trying to reduce that path length with the help of these satellites, because when we reduce the path length, distance is less, means time taken is less, so flight time will be less, fuel utilized will be less. So you are saving the fuel, you are reducing the cost, and you always obviously have the environmental application as well, because you are using lesser amount of fuel. So that's why there are all these things in civil aviation that Gagan system will help with. So that's the first navigation system that we have. Apart from that, the second navigation system is IRNSS, or Indian Regional Navigation Satellite System. Indian Regional Navigation Satellite System. So this is basically a set of 7 satellites, 3 of them which have been placed in the geostationary orbit, and 4 of them have been placed in the geosynchronous orbit. So as you can see here, you have geostationary orbit. There are 3 of them, 3 satellites placed in the geostationary orbit, and 4 satellites placed in the geosynchronous orbit. Right. So in this manner, there are a bunch of 7 satellites that are working together, and this also in a manner helps with triangulation. The same triangulation that we discussed, it actually helps with that, because see, this is one set of satellites, this becomes another set of satellites, this becomes another set of satellites, this becomes another set of satellites. So in this manner, it will also be able to use a set of 3 satellites together. That's why geosynchronous, because Geosynchronous will not be at 0 degree inclination, so above and below the equator. And then geostationary, so a set of three satellites together can be used. So this is how IRNSS works. Now, in case of IRNSS, this you can say in a manner for us is a substitute of GPS, right? We can say that this is a substitute. This is a substitute of GPS for India. So in this manner, for us, it becomes a substitute. We already see that IRNSS now instead of GPS, because GPS you might use for the maps. For example, if you're looking at a navigation or through a Google map or something, then GPS primarily is used there. But many of the mobile phone companies in India now they have started using IRNSS chips instead of using the GPS. So we already see that happening. It's not that it's in the future or it is planned. For example, Xiaomi became the first such company that started providing the IRNSS chips in its mobile phones instead of GPS. Obviously, because also it is a Chinese company, it has to be the first one to do that. Otherwise, they don't know when they will be banned. So, but jokes apart, but they became the first such company which started giving the GPS, the IRNSS chips in the mobile phones instead of GPS. So many of the other companies also have followed the suit and they also have started. Two of the biggest companies have not done it yet, and last year they were also suggested by the government that you should also start. Samsung and Apple, these are the two companies which are still using GPS, and they also have been now asked by the government of India that you should also start moving towards IRNSS and stop using GPS in your upcoming mobile phones. So this was last year. I'm not sure whether this year the mobile phones that they have launched, whether they have already started or not. I don't have the information on that, but this already is being done. So this basically is something that we see with IRNSS. So IRNSS will provide the navigation, provide the positioning, navigation, and timing services for India as well as the region extending up to 1500 kilometers, up to 1500 kilometers from its boundaries, because mainly we want to also cover the Indian Ocean region. To cover the Indian Ocean region, we need this. So this also helps us in covering the Indian Ocean region. All right. So in this manner, we see that this is something that we try to do. Now, in case of IRNSS, there are two types of services that IRNSS will provide. One called as the standard positioning service, and the second one called as the restricted service. So standard positioning service is the service that is available for every one of us. All right. Just like GPS, how we use it today, that's the standard positioning service. The second one is the restricted service, or something which is also called as precision positioning service. Precision positioning service. All right, precision positioning service. So these are the two services kind, these are the two types of services. Now restricted service will be a much more secured service, encrypted service, where the authorization will only lie with certain people. Only the people who are authorized to go into a certain areas which are sensitive. For example, areas where we have our satellites, areas where we have our missiles. So those kind of areas are sensitive zones, and we wouldn't want that everybody has the access to those areas. So that's why those kind of areas will be kept under restricted service, and only the people who are authorized to have access to those areas, only they'll be the ones with access of the restricted service. So we are doing all these things to ensure that IRNSS can become a good fit for India. The precision is not as good as GPS yet. The precision is said to be better than 20 meters, whereas in case of GPS it is 5 meters. Although now even this is being brought down to almost 10 meters with our atomic clocks. We are trying to bring it down to almost 10 meters, but even 10 meters is a good accuracy to have. Even 20 meters is a very, very good accuracy to have. And that's why we already have started using the services of IRNSS as well. Now, recently, IRNSS has been in the news because we see that there is a new satellite also that was placed into the satellite, placed into the orbit, and this basically has been used so that basically it will provide additional navigation services. So for that, this satellite was very recently launched, apart from the satellites which are already there in the orbit. Now, look at this question. This was asked in your paper. There are two questions that couple of questions that we have here. Just read the question, and then I'll give you the poll for the question as well. All right, so I'm launching the poll. It's an easy question. Please mark your answers. Yes, some of you have already given the correct answer. That's great. All right, so 54% of you have given the correct answer. I was expecting more than this. All right, so question says satellites used for telecommunication relay are kept in a geostationary orbit. A satellite is said to be in such an orbit when first is the orbit is geosynchronous. That's correct. We had discussed that geostationary is a special type of geosynchronous orbit. So that's correct. Second is orbit is circular. That's also correct. We discussed about the uniqueness of geostationary. Third is orbit lies in the plane of the equator. We discussed that it has a 0 degree inclination. So that is what it means. Fourth is orbit is at an altitude of 22 to 36. How much is it? 35,786 kilometers. I've uttered this number so many times that when you go to sleep, you'll still dream about 35,786 kilometers. So that's why this was a very easy elimination. You have four here, here, and here, right? It was a very easy elimination, so you should get this answer. So that's why I mean, just focus. These kind of you can't get these kind of questions wrong. These are easier questions to answer. Another question which we had skipped. Yeah, please read this. Again, a very simple and easy question. Yes, elimination work method. Yes, correct. This is where all the elimination methods very easily work. Right? Launching the poll. Pretty simple question again. More than 54% of you have to give the correct answer, please. Yes, already many of you are giving the correct answer. That's great. Marginally more number of you have given the correct answer. 56% of you have given the correct answer. With reference to the Indian Regional Navigation Satellite System, consider the following statements. First is IRNSS has 3 satellites in geostationary, that's correct, and 4 satellites in geosynchronous, that's also correct. So good. Statement number 1 is correct. IRNSS covers entire India and about 5,500 square kilometers beyond its borders. This is wrong. What we discussed is 1,500 kilometers beyond the Indian borders, right? So not 5,500. So this is wrong. India will have its own satellite navigation system with full global coverage. Global. What's the name? Indian Regional Navigation Satellite System. We are not bothered about global. Global is what? GPS, Global Positioning Service, right? Global Positioning System. So that's GPS, that's global. That's why it has 32 to 34 satellites. Here we have 7 satellites covering India and 1,500 kilometers beyond the Indian borders. So there's no question of full global coverage. By the middle of 2019, we are already sitting in 2023. How do you think that this is the correct answer? The correct answer will be one only. Right. So full global coverage, we are not bothered about the full global coverage. It's an Indian regional navigation satellite system. So the name itself gives you the clue that what the correct answer should be in these cases. Yeah. So apart from these, there are other satellites as well. So for example, we have satellites which are meant for space science. So there is Mangalyaan, there is Chandrayaan 1, Chandrayaan 2, Chandrayaan 3 now, Aditya L1, Astrosat mission, and the upcoming Gaganyaan mission. So these are the ones which are related to space science. So most of them, they will not be placed on these orbits, right? The orbits that we discussed, they'll be beyond these orbits or some special orbits in most of the cases. Then after that, there are experimental satellites. Experimental satellites largely will be placed in the low Earth orbit, mostly placed in the low Earth orbit. So maybe upper atmosphere, maybe 200 kilometers, 300 kilometers, just to maybe test something. Maybe test an upcoming mission, test a crucial component of a mission, maybe just environmental studies or atmospheric studies. So for all these purposes, these experimental satellites or even defense related experiments. So for all these purposes, these kind of uh, satellites will be used. Then after that, we have small satellites. So small satellites basically are the satellites which are lesser than 500 kg satellites. All right, less than 500 kg. Now in this also there is basically there are different types of satellites. So for example, the satellites between 100 to 500 kg, they are called as mini satellites. They are called as mini satellites. Generally speaking, between 25 to 100 kg, they are called as microsatellites. Between 1 to 25 kg, they are generally called as nanosatellites. And anything that is less than 1 kg, they are called as picosatellites. Right. So in this particular scenario, we see that there are all these different types of satellites. Although in all these cases, the most important one for us today becomes nanosatellites. We see that most of the small satellites that we are launching, they are largely they are nanosatellites. Some of them are picosatellites also, and very small number of microsatellites. Mini satellites, hardly we are launching any mini satellites, but nanosatellites especially are very very important. And nanosatellites, they basically also have created a market for themselves, right? the nano satellite, or let's say the uses or the advantages of nano satellites. And it's not very difficult to think that what the uses or the advantages of nanosatellites could be. Can you provide me with the points? If you don't, I will. But let's start with you. Can you think that why nanosatellites are so important? What are the uses, advantages of nanosatellites? Why is it developing as a market? Okay, cost effective. That's great. Okay, I got my first point. It is cost effective, easy to launch. Yes, that's correct. Less fuel is required. That's also correct. Can be launched many at a time. That's also correct. So, in a manner, we can talk about this being versatile and multiple simultaneous launches. Okay, that's good. Yeah, in most of the cases, experimental satellites also are nano satellites. So, okay, I'll mention this. Useful for experiments. It will not be easy to hide. It will not be so it's not that it's going to be very easy to use it for let's say spying purposes, etc. Today every country has technology that they'll be able to uh, s- will be able to identify these kind of satellites if we are launching them. Yes, time requirement. So it takes less time to construct, so that's also correct. Yes, so there is one point that I was looking for, and now I have this point. Kumari, you have provided this point. This is where just understand that apart from the specific example advantages that we have out of this, what we see as a very, very important application here is private participation. Private participation, because these satellites are easier to construct, easier to make. So that's why private players can also now enter the market. This in turn helps us create a space market. All right. So India can now become a player, a better player in the space segment. Also, it helps in employment generation. It helps in employment generation. It in turn also helps in a lot of startups also coming in this picture. A lot of startups also coming into the picture. So what we see is that there are a lot of things that ISRO directly doesn't make anymore, and it gives it to some other company, and it asks those companies to also start making things for ISRO. So that's why we see that you decrease the manufacturing cost, you decrease the manufacturing time, you can launch more satellites, you can use them effectively, you can make versatile, effective, smaller satellites. Fuel consumption is going to be less. Multiple satellites can be launched at the same time. Many companies are now developing, so there is a culture of space technology that is developing in the country. So that is leading to a lot of startups coming into the picture, a lot of employment being generated in this sector. So we see that there are a lot of things that basically, because of nano satellite market being developed, we see that this is something that we are able to do. So that's why it becomes very very crucial from that perspective, that it will be able to help in all these kind of cases. Now, pollution wise, I wouldn't still say that it is environmentally friendly. Why so? Because you still are using the fuel that we are using is hydrocarbon based fuel, so it's not environmentally friendly. Yes, amount of fuel used is lesser, but the number of launches are more, so that compensates for one big launch versus a number of small launches. So that's why I wouldn't write environmental factor being here. Lifetime is not longer, lifetime is pretty small, pretty less. Again, less space debris also I wouldn't say is the correct statement, because one individual satellite, you can say yes, that okay fine, one individual satellite will create less space debris, but the number of launches are increasing. So because of that, you are just compensating for that number. So that's why I wouldn't say that it will help in decreasing the space debris. Attracts investments, that's correct. That's why we are talking about the private participation. Okay, fine. Let me write this point. More investments in the sector. So yes, FDI is basically being the part of the same, as somebody had mentioned. Boost research and development, that also is correct. You can say that it will help in more research and development. And basically that is what I meant by when I wrote here useful for experiments. So I'm just mentioning here itself, more R&D. All right. So we see that there are n number of things that they will help with, and that's why we have seen that there has been a huge growth in the space market. And because of that, now we see that there is a special launch vehicle that India has, which is called as small satellite launch vehicle. Small satellite launch vehicle, or SSLV. So that's the reason, because we also have identified that for India it will be very very crucial. Similarly, now we have something called as NSIL, New Space India Limited. Then apart from that, you have In Space. So all these are also working together, so that they will help in more setup of a better space market in India. And last year, for example, when ISRO launched PSLV C51 and 52, they also had mentioned that the parts that have been used in the launch or these satellites, they have not entirely been made by ISRO, but there are other companies which have made it. They, for example, they mentioned about Bharat Dynamics Limited. They mentioned Bharat Dynamics Limited. Similarly, there are other companies also which are working with the government of India, with ISRO, etc. So, for example, there is Masdoc, or you have other companies like Paras in defense. So there are other companies also which have started working. And as soon as they took the name of Bharat Dynamics Limited, just check the stock prices of Bharat Dynamics as an exercise. I think it was February 2022 when they announced that Bharat Dynamics Limited has made parts for them. Bharat Dynamics Limited, the stock price for them was around 200, 250, I think, back then. And from there on, it has just launched. and it is above 1000 if I'm not wrong. So all these, so that's why the stock market also took, I mean, their stock prices also rose, because ISRO announced that they are using the services of Bharat Dynamics. So in this scenario, that's why we have seen that all these kind of developments have happened in the field of small satellites. So this from the mains perspective, remember this, all these points from the mains examination perspective will be very very important. And then lastly, we also have university or academic institution satellites, because so these are the satellites that have been developed by some college, some university, students and faculty, they come together, they make these satellites. Most of these satellites will be nano or pico satellites, and once they develop them, the launch will be done by ISRO free of cost. ISRO launches these satellites with no charge, because ultimately they also want better participation of the students as well, because these students, today if you nurture them, tomorrow they are going to help you. So tomorrow they might, even if they, let's say they don't join ISRO, but at least they might become a part of the space market, and that will itself help in better growth of the space technology in India. So that's why we see that all these kind of things are also done by ISRO to help in further uh, development of this. So next is Lagrange points, but we'll not start Lagrange point today. We are almost done with the time. Look at this question. I forgot to correct this. This has to be 1, 2, and 3. And C has to be 3 only. Read this question, please. So I'll launch the poll for you. So 50% of you have marked D, which actually is the correct answer. I mean, when I made this correction, many of you might have gotten the answer there itself. But okay, so let me discuss this. For the measurement or estimation of which of the following satellites of the following are satellite images or remote sensing data used. First is chlorophyll content in the vegetation of a specific location. So the question basically is asking, would we be able to understand what is the amount of chlorophyll content in the vegetation of a particular region? Yes, we can. How exactly? We analyze the green color. We analyze the green color, and this analysis of the green color is something that will help us in identifying this. All right, so if the intensity of green color is very high, then it means that this is an area which has larger amount of chlorophyll, meaning that it is able to use the water and nutrition provided in that area very well. So it has very good applications in agriculture. So we can use uh, the remote sensing satellites to actually identify this, and this is doable. This is something that we do, and that helps our agriculture. All right, so that's the first thing. Second, greenhouse gas emissions from rice paddies of a specific location. So in the rice paddies, what kind of greenhouse gas emission happens? Which greenhouse gas will be emitted from the rice paddies? Yes, methane. Correct. Perfectly correct. So it basically is about identifying methane. Can we identify methane? Again, the answer is yes. We can actually identify the presence or presence of any gas and even the amount of a certain gas that is present in any given area with the help of our satellites. And that too will be done with the help of imaging. When we take the pictures, the images of any given area, that will give us an idea about the greenhouse gas emissions as well. So that's doable. Third is land surface temperatures of a certain location. Now, land surface temperatures basically means heat. Correct. We are trying to understand the amount of heat that is being generated, and this is something that we can actually understand from infrared rays. So this will be about identification of infrared radiations. How much of infrared radiations are being emitted from a certain place, that will give us an idea, and that also can be done. And all these basically can be done with the help of satellites. There is a specific type of satellite called as, which we had launched, called as hyperspectral imaging satellite. The hyperspectral imaging satellite can do all these things. All right. Hyperspectral imaging satellite can actually do all these things, mainly because hyperspectral imaging, and this, the name, that's why this satellite is called as HISIS, hyperspectral imaging satellite. This was launched in 2018 and this question was asked in 2019. So in a manner it was a current affairs question which has been camouflaged as a direct satellite based question, but actually it was a current affairs question. But this is where you have to understand that how to read current affairs is very very important, because look what's happening here. They did not ask you what is hyperspectral imaging satellite or what is the use of hyperspectral imaging satellite. Even if you look at the newspapers, you will hardly find any information about what is hyperspectral imaging. If let's say if India is launching a hyperspectral imaging satellite, the very first question that should come in your mind is, what do we mean by hyperspectral imaging? What is hyperspectral, or what is hyperspectral imaging? See, normal image that our eyes capture, we basically are able to capture the primary colors. All right, we only capture, or our eyes only capture the primary colors, red, green and blue. All right, when we say hyperspectral imaging, that's the kind of imaging where uh, every part of the electromagnetic spectrum is involved: radio waves, infrared rays, x-rays, visible light, every color in this visible light. So every part of the entire electromagnetic spectrum can be used for imaging. So that is what we call as hyperspectral imaging. All right, so that's basically is something that can be done here, and we actually use it for getting the satellite images, and that's why the correct answer will be 1, 2 and 3. Right, so let's stop here. The next topic for us is Lagrange points, something that let's start in tomorrow's class. And after this there are small portion that is left, so tomorrow we'll be able to complete this portion and we'll start with our next chapter, which is energy. So energy will be the second chapter that we will start tomorrow. So now if you have any questions, please let me know. Let me discuss them with you and then we shall end the class for today. The leaderboard. Okay, leaderboard. Yes, so this is the leaderboard. There are three of you who have everything correct. So Karthik, Akshita, and Aniket. Congratulations to all three of you. And everyone else, not a bad job. Even if you are getting 7 or 6 out of these 8 correct, it's a wonderful job that you've done. Good to see.